Let's discuss one of the simplest oscillating systems of a physical nature called a simple pendulum. A simple pendulum consists of a bob, this mass at the end, which is usually spherical, and attached to that bob is a string. Now this string goes all the way to wherever you're supporting it. In this case, I just drew it as a little support point. I'm going to call the length of the string part alone script L and the bob's radius as capital R. Now, if you go back to the previous videos, you will find the theory of the physical pendulum. So the oscillation angular frequency, omega simple harmonic, is the square root of the mass times the acceleration due to gravity times the distance between the center of mass of the physical pendulum. We're going to assume the thread has got no mass, so the center of mass is located exactly in the middle of the bob, to the point of pivoting. The pivot point is where it's attached, P. So that distance is called D. So it's mgd divided by the moment of inertia of the physical pendulum about the pivot point P. Now let's try to write an expression for both d and for I sub p. The distance d from geometrical considerations, just by looking at the figure, is L plus R. The moment of inertia of a spherical, now usually pendula, the plural of pendulum, they're usually made out of a solid object like iron, for example. So I can think of this as a solid sphere. So the moment of inertia about point P is the moment of inertia about the center of mass plus md squared according to the parallel axis theorem, and I can use the moment of inertia of a sphere, solid sphere, for the moment of inertia of this bob about the center of mass. It's 2/5 mr squared plus the distance between the center of mass to the axis of rotation. The actual axis of rotation is P, whereas the old axis of rotation is the center of mass, and that distance is D, which happens to be L plus R. So that's m times L plus R squared. So already it's looking pretty complicated for something whose name is a simple pendulum. Let's see what we can do with this though. I'll put this back in this formula. Omega simple harmonic is equal to the square root. Now you'll observe that I sub p has got factors of m, which will cancel the factor of m there. So I'll just not write the factor of m anymore. It's g times d, which is L plus R, divided by 2/5 mr squared. Oh, no more m's. 2/5 r squared plus L plus R squared. That is fairly complicated looking. Let's write the period of this pendulum, T simple harmonic. That's going to be 2 pi divided by omega simple harmonic by definition of what period means. So that's 2 pi square root. Here I have a complicated expression. I'll try to simplify it a little bit. Let me take the square of this term. It's going to be L squared plus 2RL plus R squared, and then I have 2/5 R squared, which is actually 0.4. 2/5 is 0.4 R squared, divided by G times L plus R. Here's where I'm going to make some approximations just to see how I can simplify this a little bit, because it looks fairly complicated right now. And that approximation is this. I'm going to take R to be much smaller than the length L. That's usually true for a simple pendulum. We normally try to keep the length around 0.5 meter or so. Since I'm going to investigate how small we can keep it, I should not put r equal to 0, because then if I put r equal to 0, it'll go back to being, so let me just indicate what happens when r goes to 0 first. This becomes 0, that becomes 0, that becomes 0, so I just have L squared over here, and in the denominator I have G times L. It goes back to the classic simple pendulum formula for a point bob mass. So I'll call that the point bob. The point bob is not terribly interesting. What I want to analyze in this video is how small can you make this to get some suitable error from that point bob approximation, like say a 5% error. How big can that bob be in relation to the string to be only off by 5% from this point bob? Let's make that our goal. Need 5% error. And that'll inform us as to how big a bob can be used in relation to the string length in an actual experiment. All right? So that's the point bob, and that's the reality. Now what we can do is neglect r squared, okay? Because we can't neglect r, otherwise we'll just end up with a point bob, but we can certainly neglect r squared. So I'm going to do that and proceed as though r squared does not exist. So t simple harmonic is now 2 pi square root of L squared plus 2RL divided by G times L plus R. Now I just have single factors of R, so I cannot play any more games. At this point, let me just try to find the difference. This is, let's call this T point. So remember, what I'm trying to do is T simple harmonic minus T point divided by T point has to be 5%, which is 0.05. So that's my goal, to get a 5% error in this approximation. So that T point over T point is 1. So what I'm going to write this as is the following: T simple harmonic over T point equals plus minus 1 equals 0.05, and then I transfer the minus 1 to the other side, so it becomes a plus 1. So I get T simple harmonic over T point equals 1.05. Let me square this, because I notice all these square roots, so I don't want those square roots. I'm going to square that. So I'll get T simple harmonic squared over T point squared equals 1.05 squared. The 1.05 squared is 1 plus 0.05, the whole thing squared. So you can use your basic formulas to do that. A squared plus 2ab plus b squared. So 2ab is going to be 0.1, because it's 2 times 0.05 times 1. And b squared is going to be much smaller than 1, so I'm going to neglect b squared. I'll write it as plus 0. So this is a new kind of mathematics where all the equal signs have to be taken with a grain of salt. So that's 1.1. Now on the left side I have t squared, so let me just substitute that. I'll forget about the factors of 4 pi squared. You're going to get a 4 pi squared here, and you're going to get a factor of 4 pi squared there, the factor of gravity there, factor of gravity there, all that. It's planet independent. So I'm just going to end up getting, when I square this, I'll end up getting L squared plus 2RL divided by L plus R, and when I square that, I just get an L, and that all has to be equal to 1.1. So we're getting somewhere now. The L's can be cancelled, and now I have this wonderful little equation that's telling us something really interesting. L plus 2R is equal to 1.1 times L plus R. So let's press on. L plus 2R equals 1.1 times L plus 1.1 times R. Now I can take this 1.1 R to the left side, so I'll get 0.9 R, because that's what 2 minus 1.1 is, it's 0.9. And this L I can take to this side, so that becomes 1.1 minus 1, which is 0.1 L. So that gives us R must be equal to 0.1 over 0.9 L. In other words, R must be equal to 1/9 the string portion of the pendulum. Now the length of a pendulum is simply defined as D. So that's going to be L plus R. So the length of the pendulum is just L plus. So I want to write this as in terms of the length of the pendulum. This little L. So what I'll do is this. Little L is the length of the pendulum minus capital R. So let me substitute that in here to get a statement about what the length of the pendulum must be in terms of the radius. So I get here the radius equals 1/9 the length of the pendulum minus the radius. So if I bring this side, I'm going to get 1 plus 1 over 9 times the radius equals 1/9 D. And after some simple fractions, this can be written as 9/9. 9/9 plus 1/9 is 10/9. 10/9 R equals 1/9 D. So it tells us that the radius of the bob must be equal to 1/10 the pendulum's length. Overall length. So to put it in concrete terms, if you have in your lab a bob that is about 1 centimeter in diameter, this is typical of our labs in our IT. You have these pretty beefy looking balls that are 1 centimeter in diameter, and you make a pendula out of them. Then if you don't want to see really bad results, you're strongly advised to keep the pendulum length at least 10 centimeters. Now 10 centimeters drawn to scale is this big. And it's a fair bet that almost no student goes shorter than this for a pendulum.